Hello and welcome. We have studied the unit of rational functions, and our first lesson was on graphing the reciprocals of a linear function. A few things that we observed was that number one, reciprocals of linear functions have two asymptotes, one horizontal and one vertical. I'm going to start with horizontal asymptotes because they're always the same. Y equals 0, or the x-axis, for all of them. On the other hand, the vertical asymptotes are always located at the restriction of the reciprocal of a linear function. So in these first two examples, the restriction is at 0, the vertical asymptote is at x equals 0. In these next two examples, we have restriction at 3 over 2, then the vertical asymptote is at x equals 3 over 2. Restriction is at x equals 2, vertical asymptote is at x equals 2. And then the graphs of reciprocals of linear functions will simply follow their asymptotes. And we discussed how to find these points and where the graphs are located. Today we'll continue with reciprocals of a quadratic function. And before we start graphing them, a few things that we can talk about and discuss together. Number one, to find the vertical asymptotes, we always inspect the restrictions of the function. And I should say of the reciprocal, and we're very soon going to change this word to rational. The equation of the vertical asymptotes, though, then is the vertical asymptote is x equals wherever the restriction is. Now, when you think about how many possible zeros quadratic function has, then you'll say that, well, there are quadratic functions that can have two zeros or two x-intercepts. So we can say possibly two. Some quadratic functions can have only one zero, like in these two examples here. So you can say possibly only one zero. And some quadratic functions can have no zeros at all, like these ones here. And in this case, we say none. Now remember that the quadratic function will be in the denominator, and the zeros of the quadratic function will play the role of the restrictions. And the restrictions of the denominator will make the vertical asymptotes. So they are all connected to each other. So we're going to say that the quadratic function, or the restrictions of the reciprocal of quadratic functions, can be two of them. So reciprocal quadratic can have one restriction or no restrictions. As a result, the reciprocal of a quadratic function can have two vertical asymptotes when the denominator has two zeros, or when the reciprocal has two restrictions. It can have one vertical asymptote when the denominator has one zero, or the reciprocal has one restriction, so one vertical asymptote, or the reciprocal can have no vertical asymptotes at all. And that happens when the quadratic has no zeros. So the reciprocal of a quadratic has no restrictions, and that makes the graph of the reciprocal have no vertical asymptotes. So let's start graphing the first example. I've chosen the reciprocals of quadratic functions with one restriction to start with. They're the easier one to understand. So we have the function gx equals x squared. That is a quadratic function. And we are finding or graphing the reciprocal of 1 over gx So 1 over x squared. So if you graph g of x, remember the vertex is at 0, 0. And from the vertex, we simply follow the step pattern. So 1 over 1 up 1, over 1 up 3, over 1 up 5. So here we go, here we go, here we go. And there goes a beautiful, beautiful parabola. Okay. Fantastic. So this will be g of x. Remember that the reciprocal of g of x is the reciprocal of all the y values on the graph of the parabola. So the y values on the graph of this parabola are 0, 1, 4, and 9. So we're going to reciprocate them to create a graph of 1 over x squared. The reciprocal of 1 is still 1. So we're going to say this will be a point on the graph of the reciprocal. The reciprocal of 4 is 1 over 4. So this will be a point on the graph of the reciprocal. Reciprocal of 9 is 1 over 9. So this will be a point on the graph of the reciprocal. Now when you think about it, as x approaches infinity, that's where x approaches infinity, the y values will approach 1 over infinity squared, or simply 1 over infinity, or we're going to say 0 plus, which means that all the points of this graph will be slightly bigger than 0, and the graph will approach the x-axis very close and never touch it. And now we're going to check and see what is happening in this interval. Remember that here we're approaching 0, and x cannot equal 0. Say, for example, we're at this point where y value is 1/2. The reciprocal of 1/2 will be 2. So this will be a point on the graph of the parabola. Let's say that here the y value is 1/4 for the parabola, for g of x. For reciprocate 1/4, you get a 4. Now, if you allow x to approach 0 from the right side of it, this is 0 plus, right? This direction, then the y values will approach 1 over 0 plus. And dividing 1 by 0 plus gives infinity. So we'll say that as the graph, or as x approaches 0 from the right side of it, then the y values will increase to infinity. This will be one side of the graph of the reciprocal of a parabola. Now, in the same way, we reason about the other arm. Notice that the y values here are the same as the y values of the other arm of the parabola, so we're going to see a symmetrical shape. You can tell that this function has even symmetry, so the y-axis will serve as the line of symmetry. So similarly, we're going to say that when y equals 1, reciprocal of 1 is 1. Y equals 4, reciprocal of 4 is 1/4. When y equals 9, reciprocal will be 1/9. And as x approaches negative infinity, the y values will approach 1 over negative infinity squared, which is 1 over infinity, which again is 0 plus. So that tells us that the graph will approach 0, but from above, because it's always going to be slightly bigger than 0. Now we're going to take a look again at what happens in here. So say, for example, that here the y value is 1/2. That means that for the reciprocal, we're going to have y value, the reciprocal of 1/2, 2. Reciprocal of 1/4, 4. We are approaching 0, remember, here from the left side of it. So we're going this way around. And we're going to say that as x approaches 0 minus, the y values will approach 1 over 0 minus squared, or 1 over 0 plus. And that, my friend, is infinity. So we are going to say that as x approaches 0 from the left side of it, the y values will go up to infinity. Now, we are going to discuss the asymptotes at this point. I wanted to shape the graph first, because that can make the asymptotes a bit more obvious for us. Now, what are the asymptotes? Remember, in linear functions, we said that the asymptotes are always a restriction of the denominator. That will never change, no matter how complicated or involved the rational functions or the reciprocal functions become. So we're going to say that in this case, the restriction is at x equals 0. So we're going to say more precisely, x has to be different than 0. Therefore, the vertical asymptote will be at x equals 0. So let's draw the vertical asymptote right here. And whenever you draw the asymptote, write down the equation of it, vertical asymptote, x equals 0. Now, this rational function, or the reciprocal of this quadratic, will also have a horizontal asymptote. So, horizontal asymptotes are always created when the y values stop changing, no matter how big or small x becomes. So in our case, we say that as x approaches infinity, the y values, so as x approaches infinity, the y values will go towards 0, and they are not going to change. And we're going to say that at y equals 0, the graph has built a wall, a horizontal one, that will not allow the graph to cross to the other side of it. So this will be the horizontal asymptote. And it's again, it's best that we label the asymptotes by their equations. So y equals 0. And this is the graph of the reciprocal of a quadratic with one x-intercept. So a quadratic with one x-intercept, or a reciprocal with one restriction. Okay? Now we're going to move on to the next graph. As you can see in here, we're still graphing the reciprocal of a quadratic. Now let's take a look at the number of restrictions. Now remember that as we take more and more examples, we are going to discover shortcuts and faster ways to graph reciprocals of a quadratic or any rational function, okay? So as our understanding about them, about the behavior of a quadratic or rational function or reciprocal quadratic evolves, then we can graph them much faster and much better. Okay, because we have more tools in our hands, right? So this time I'm going to approach this a bit differently, because I recognize the fact that this is a reciprocal of a quadratic with only one zero, just like the previous example. So I'm going to say, well, I know that quadratic functions in here can produce restrictions. Okay, can. How many in here? Only one. So we're going to say that the restriction here is x different than 2. For those of you who want to see it a little bit better, this is 1 over x minus 2 times x minus 2. So you have the same restriction produced by each factor. So therefore, so this is the restriction, the vertical asymptote will be at x equals 2. So I'm going to draw the vertical asymptote right at x equals 2. Now, whenever I see that there is a constant in the numerator, that makes me think, the numerator is a constant number. And it doesn't have to be just one. It can be any constant number. It can be 2, 3, 4, any positive, can be a decimal, it can be a negative number, a negative decimal, it doesn't matter as long as there is a constant different than 0. Now, whenever you have a constant number and you divide it by a number no matter how big or small, that will never equal 0, so it will either be 0 plus or 0 minus. Okay, it will never equal 0. So we're going to say that the horizontal asymptote will always be at y equals 0. And did I say that we have to label our asymptotes by their equations? So let's do that. So x equals 2 is the vertical, and y equals 0 is the horizontal asymptote. And now we're going to shape the graph of this function. We're going to say that this function here, 1 over x minus 2 squared, must follow its asymptotes. So if we were to graph x minus 2 squared, we could easily see here that the graph will go this way. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Here we are. And the reciprocal of 1 in here will still be 1. The reciprocal of 4, 1/4. Reciprocal of 9, 1/9. I now know what the shape is, so I draw it with more confidence. And I know that as x approaches 0 from the right end of it, I will show some calculations. So we are going to have 1 over the 0 here is at 2. Okay, so then we'll have 2 from the right minus 2 squared. Now, 2 from the right means 2.000. You can add as many as you want. 1 minus 2 squared. So that will make this expression 1 over 0 plus squared, or 1 over 0 plus, or infinity. So the graph will approach infinity. In the same way, we reason about the other side of the graph. So y equals 1. For the reciprocal, it's going to be 1. So y equals 4, reciprocal 1/4. Y equals 9, reciprocal 1/9. So the graph is going this way around. And I want to show what is happening in here as x approaches 2 from the left end of it. So we familiarize ourselves with how to use this process in more complicated functions. So we're going to say that as x approaches 2 from the left side of it, and I'm going to take an example, 1.999, then the y values will become 1 over 1.999 minus 2 squared. So that will make the function equal to 1 over 1.999 minus 2 is 0 minus squared. So this in return will be 1 over 0 plus, because 0 minus squared, like negative 0.000001 squared, is a little bit more than 0. So that will make y equal to infinity. So we now know that the graph will go all the way up. And here goes the graph of this reciprocal function with two sides of it, with two pieces separated by the only vertical asymptote that they have. Now, we're moving on to the second type of graphs, reciprocals of a quadratic function, but this time with two restrictions. So as an example in here, I'm taking the graph of the parabola gx equals x minus 2 times x plus 3. And we will reciprocate it. Let's make this Rectangle, perfect. All right, we'll reciprocate it to create the graph of f of x equals 1 over x minus 2 times x plus 3. Let's make the screen a bit larger. Here we can see it better. Okay, so let's graph g of x equals x minus 2 times x plus 3. Remember that this will have two zeros. 1 0 will be at x equals 2, and 1 0 will be at x equals negative 3. So these will be the x-intercepts of the parabola. So negative 3 goes here, positive 2 goes here. And now we're thinking, how far down is the vertex? So we can draw the graph of the vertex, no problem. And we're going to say here that the vertex must be halfway between negative 3 and positive 2. And halfway between them is at negative 0.5. So we know the vertex will be somewhere in here. We don't know exactly where though, because we don't know what the y value at the vertex is. So we find the y value at the vertex by substituting the x at the vertex, which is negative 0.5. Actually, let's make this red so we remember where we got it from. And if you do the calculations in here, then you will find out that negative 0.5 minus 2 times negative 0.5 plus 3 will give negative 2.5 times positive 2.5, which is 6.25, I think. Negative. So 1, 2, 3, 4, 5, 6. Oh gosh, 2, 4, 6. Okay, so we're going to be somewhere here. That's okay. So we're just going to sketch this. We're not drawing it accurately because that's where the x-intercepts of the parabola will be. Okay. Now we're going to say that wherever the x-intercepts of the parabola were, the graph will have the reciprocal will have the restrictions. So we're going to say that there is one restriction at x equals 2 and one restriction at x equals negative 3. Therefore, we're going to say that there will be a vertical asymptote at x equals 2 and another one at x equals negative 3. And we're going to draw this. The graph will also have a horizontal asymptote at y equals 0. And the reason why is because y will always be different than 0 due to the numerator being a constant number. Whenever the numerator is a constant number, then the horizontal asymptote will be y equals 0, because any constant number divided by any quantity, big or large, large or small, I meant, can never equal 0. Sorry about that. So, well, it's 4:34 in the morning, by the way. So we are going to say that the horizontal asymptote is y equals 0. So we're done with the asymptotes. All we have to do now is shape the graph. We're going to follow a more sophisticated approach to graphing this. I would like us to bring our focus here on this portion of the graph. What you see in here is an increasing quantity. The y values are increasing. So when the y values are increasing, the reciprocals must be decreasing. So if you think of the y value, let's say, for example, at this particular point, say 1, 2, 3, then the reciprocal will be 1/3. And as x values increase to infinity, the y values will approach 0. Similar to this, as the x values approach 2 from the right side of it, from the right side of it, the graph will have to go up. And this is how we explain this. Remember that when x approaches 2 from the right side, which is where the asymptote, the vertical asymptote is, we can take a value of x 2.001, and we'll say that the y values would equal 1 over 2.001 minus 2 times 2.001 plus 3. So the y values will be 1 over, this will give us 0 plus, because we have a number slightly above 2, take away 2. And this will be some constant positive number, 5 and a little. And that's what I'm going to write, a constant positive, because it doesn't matter how big or small this is. All we look at is the sign of it, okay? Because when you multiply it by 0, that will become, the whole thing will become a 0, right? But the sign can change the story. If it is a negative in here, then it will be a 0 minus. Now, in this case, we have positive, so that's a 0 plus. So we have 1 over 0 plus, which is infinity. So that's how we think about the values of y for this section of the graph. Now, in the same way, we can reason about the other part of the graph here, because you can see that something similar happens. So the y value here at this point, for example, let's say it's 3. The reciprocal will be 1/3, somewhere here. As we approach negative infinity in this direction, so as x approaches negative infinity, the y values will be 1 over negative infinity times negative infinity, because you add or subtract anything to negative infinity, then that will be still negative infinity. So this will be 1 over infinity, or 0 plus. So we'll say fine, 0 plus it is. This is where the graph is going, so close to, here we go, very close to the x-axis. Similar to this, the graph has nowhere to go here because it's hit by the asymptotes. So it will go all the way up. And now we have to discuss only this portion of the graph in here. Remember that in the reciprocal, when we had only 1, 0, we didn't have room between two vertical asymptotes. So nothing happened in between. We only saw these two sides, or these two pieces. And this is where they are in the reciprocal of a quadratic with 2 zeros. But because there are two vertical asymptotes in here, there is stuff going on between the two asymptotes. And we're going to check and see what is going to happen here or here. Now, we're going to focus on the parabola because that's what we are reciprocating. I'm going to look at some key points in here. So this vertex here is negative 6.25. So if you reciprocate this, it will be 1 over negative 6.25. So it's going to be a point somewhere in here. If you reciprocate this point at y equals negative 4, then we'll say that we're going to have 1/4 negative. The same thing with the other side of it, 1/4 negative. So the graph looks like this. I'm exaggerating this a little bit because it's hard to scale. And remember that we're only sketching these graphs or predicting their behaviors. So now let's check and see what's going to happen as we approach positive 2 from the left end of it, from the left side of it. When we approach x from negative 2, when x approaches negative 2, positive 2 from the left end of it, then that means x is something like 1.999, right? So the y values will be 1 over 1.999, take away 2, times 1.999 plus 3. So that will make the y value equal to 1 over 0 minus times a positive number. So that would be 1 over 0 minus, or negative infinity. So the graph will go all the way down here. And similar to this, we're going to find that it has to go this way. It's not going to cross the asymptote, so there is no other way to go for the function. And this will be the graph of the reciprocal of a quadratic with 2 zeros. Now, as complicated as this process seems, once we understand the behaviors, we're going to classify the graphs. We'll recognize what the shape of the graph is just by looking at the equation. So in equations, when you have a constant, you always have a horizontal in the numerator. You will always have a horizontal asymptote at y equals 0. Your vertical asymptotes are always found by simply finding the restrictions. And as soon as you find where a point on the graph is, for each side of the vertical asymptote, this is the vertical asymptote, it has the right and the left side of it, right? So this is the right side and this is the left side of it. So you give x a certain value and find the value of y, you're either going to find a y that is positive or a negative. If you find that the y is positive, then you're going to say the graph has to be here. Because if a point of the graph is in here, then the rest of the points have to be nested inside the asymptotes. And rational functions actually are nothing but curves that follow their asymptotes. You do the same thing with this section in here. So you are in between two vertical asymptotes, so the graph will either be here or here. If you want to find out where the graph is exactly, give x any value within the two vertical asymptotes. And if you find that the x values are below the x-axis, that means that the graph will have to go down in here because it has to follow the asymptotes. It has no other way to go. And the same thing happens to the other piece. So when you have 2 zeros in the reciprocal of a quadratic, then you will see a three-piece graph, which is very similar to this reciprocal with one vertical asymptote. But here we do not see, in the reciprocal with one vertical asymptote, we do not see what's going on between the two asymptotes because they're squeezed in together. Now, you can definitely try to graph the next function, mx equals x squared minus 4. That's the quadratic, and you can graph the reciprocal of it by quickly drawing the asymptotes. So the faster way would be x different than 2 and different than negative 2. That's a restriction. That makes the vertical asymptotes x equals 2 and negative 2. So I would draw the asymptotes. And for the horizontal asymptote, I'm going to say that numerator is a constant number. So that means that the y values will always be different than 0. That means that there will be a horizontal asymptote at y equals 0. And I will draw the horizontal asymptote here. And label the asymptotes by their equations. It's vertical, obviously it's a vertical line. And this is y equals 0 and the horizontal asymptote. Now, I want to draw the graph of this reciprocal here. And I don't want to go through the whole tedious process of drawing the parabola and so on. So what I'm going to do is think. Here is a vertical asymptote. Here is a horizontal asymptote. So if I have a vertical and a horizontal here, the graph will either be here or here. I'm looking at the right side of the vertical asymptote. So let's give x some values in this interval. Say, for example, x equals 3. At x equals 3, the y value will be 1 over 3 squared minus 4. So that's 1 over 5. That's a positive number. That means the graph will be in this room, kind of. You can look at them as like the rooms where the asymptotes, where the graphs will sleep in at night or during the day, whatever they feel like. All right. So the graph will have to follow the asymptote. Done. And now I'm going to check the left side of this asymptote. So what's going on? And I'm going to give x a certain value. Let's say x equals 1. At x equals 1, we have the y value equal to 1 over 1 squared minus 4. So that would be equal to negative 1/3. So at 1, we have negative 1/3. And because of the symmetry of this graph, I'm going to say negative 1/3 in here. I'm curious to know what happens at x equals 0. That would be negative 1/4. Because imagine this being 0, right? So 1 over negative 4, that would be the y-intercept. And you see, when we do the graph analysis, the intercepts will be some of the critical points that can guide us where the graph is going. Now, do we have to do those 3 plus or 3 minus or 2 plus, 2 minus, or whatever we did here with the asymptotes? Not necessarily, because we now understand the behavior of functions that have 2 restrictions. And we're going to say there is an asymptote in here, an asymptote in here, another horizontal here, and the graph is here. It has nowhere to go but follow the asymptotes. And you can shape the graph very easily this way. Again, things are done with some accuracy, not with precision. And the last thing we need to look at is this vertical asymptote. So we already did the right side of this asymptote. Now we have to do the left side of it. So we're going to take a value, negative 3, and we're going to substitute it into the equation. So at x equals negative 3, y would be 1 over negative 3 squared minus 4. So that's 1/5. So we're going to say, okay, so the graph had this vertical and this horizontal asymptote. And it could have been either above the horizontal or below, right? Because we're checking the left side of the vertical. And then we're going to say, well, it's above the horizontal asymptote. And if it is in here, it has to follow these 2 asymptotes, this portion. And then here we go. There goes the graph of this reciprocal. X squared minus 4. That's the parabola, and the reciprocal of it will have these 3 pieces. I hope you're ready for one last one. I know this has been a long video. We're going to do this example together. It's x squared plus 4, the parabola, and we are reciprocating this parabola, so 1 over x squared plus 4. Now let's take a look at the restrictions. We're going to say that x squared plus 4 different than 0 if x squared is different than negative 4, And we find out that there are no restrictions in here. And no restrictions means no vertical asymptote. So we'll leave with that. Now for the horizontal asymptote, we have to check with the y values. We're going to say the horizontal asymptote is y equals 0 at y equals 0 for the same reason we said that the horizontal asymptote was at y equals 0 in the other reciprocals, because a constant divided by any number, no matter how large or how small, will never equal 0. Now, in this case, I'm going to ask for help the graph of x squared plus 4. And the reason why is because it has no vertical asymptote, so I don't know how to check beyond it. So here goes the graph of x squared plus 4. It has the y values at 4, 5, and 8 in this case. We can continue on forever, obviously. And we will reciprocate it. We have already discovered the horizontal asymptote at y equals 0. And we'll say that if you reciprocate the y value of 4, that will give 1/4. So it will be a point in here. If you reciprocate 5, that would be 1/5. I really have to make this super big. And if you reciprocate 8, 1/8. And you can continue on the other side, reciprocate, reciprocate. So let me make this bigger. And we're going to say that if x approaches negative infinity, then the y values will approach 1 over negative infinity squared plus 4. So that's 1 over infinity or 0 plus. So the graph will continue approaching the horizontal asymptote this way. In the same way, we're going to say that as x approaches positive infinity, the y values will be 1 over infinity squared plus 4, which is practically 0 plus. So the graph will approach 0 plus this way. Now notice that there is a rise on the graph of the function here, a smooth one. Excuse me, and this will be the graph of it. So no vertical asymptote. Now imagine if there was a vertical asymptote, the flow of this graph would have gone, so if the vertical asymptote was here, then the graph would have gone close to the vertical asymptote, and then it would be hit by this asymptote, so it would have had to continue the path upwards, right? Because the vertical asymptote wouldn't let it continue the flow the way it was before. So because of this, and because of the lack of the vertical asymptote, the graphs will join in here and make a nice smooth curve. And that would be the behavior of it. Now let's take a look at a better version of the graph in there, because that was obviously a little bit small. So we're going to graph 1 divided by x squared plus 4. Okay, so at least Desmos is a bit more convenient when it comes to looking at the shape of the graph. So I'm stretching this so that we can see what the shape of the graph is, just a tiny bit better. So you see the curve will go up at here, this point in here, 0.25. Okay, so there is no vertical asymptote in here. That's why the graphs will join each other at this point. So that would be the shape of it. Beautiful, isn't it? So in the same way, we are going to graph the function 1 over negative x squared minus 2. So what we have in here, remember, is the graph that opens down, a parabola that opens down. So that's negative 2. Here is negative 3, and here is negative 6. You reciprocate negative 6, you get negative 1/6. You reciprocate negative 2, you get negative half. You reciprocate negative 3, negative third, negative third, negative 1/6. So you can see that as x approaches infinity here, the graph has to follow the horizontal asymptote, because you see we have a 1 in the numerator, so y equals 0 will be the horizontal asymptote, and the graph will approach the horizontal asymptote, but from below this time. Okay, and if you want to actually discuss or see why it approaches from below, which is kind of interesting actually, it's something that you're going to do more in calculus more often when you describe the end behaviors and we find the limits. But here it goes. It's not too difficult for you to understand. So I'm going to let x approach infinity. So we have negative infinity squared minus 2. So negative is outside the square, right? So that would give negative infinity minus 2, or 1 over negative infinity. So 0 minus will be the values of y. That's why we see the graph below the x-axis. And obviously you can see it from the other point of view, so it's reciprocal of negative 6, right? So there is no way we can get this wrong. So just to summarize everything, and I come up with this idea actually only recently. I think it's important that whenever we learn something new, we kind of sort that out in our head and we try to find a place to store it in our head. And the best way to do it is by reflecting on whatever we just learned. So today's lesson, we're going to say, was on graphing the reciprocals of linear and quadratic functions. Sorry. Actually, I have a bright idea. Not so bright, but I'm going to make it green. So the reciprocals of linear and quadratic functions. Let's see, we have room here. Okay. And the different cases we investigated were the reciprocals of linear functions, the reciprocals of quadratics with one vertical asymptote, reciprocals of quadratics with two vertical asymptotes, and reciprocals of quadratics with no vertical asymptotes. Now the graphs of reciprocals are characterized by their asymptotes. And actually, the reciprocals of functions all are curves that follow their asymptotes. That makes them so special. And so easy and complicated in the meantime, right? But once you understand the tricks of them, like it's kind of easier, like a lot easier. Now, all graphs of the reciprocals will have the same horizontal asymptote, always. And please remember this, it's very important. It will make your life easier. And the equation of it is y equals 0. The graphs of reciprocals may also have vertical asymptotes. And I say may because, we saw a reciprocal of a quadratic with no vertical asymptote as well, right? So may also have vertical asymptotes. So to find the equation of the vertical asymptote, we follow two steps, very simple ones. So first we found the restrictions of the denominator. And then we stated the vertical asymptotes with equations x equals wherever the restriction was. Now, the domain of the rational functions is related to the vertical asymptotes. See, and the domain will be any real number x such that x is different than whatever the vertical asymptote is. So they're interrelated. So once you know the domain, you will know where the vertical asymptote is. When you know the range, you will know where the horizontal asymptote is. So the range is related to the horizontal asymptote. And we say that is any real number y such that y is different than the horizontal asymptote. And this is it for today. I know it was a very long lesson, but I hope it made sense, and I hope that it helped you understand reciprocals of linear and quadratic functions a little better. Bye for now. I'll see you next